Next, I think we can go off for a case where there is a particle that is hitting a spherical ball and it's a off-center collision. So the term that we have for such kind of collisions is oblique central impact. So let us say that there is a spherical ball. There is a spherical ball somewhere like this, and this ball is kept on a horizontal surface so that it doesn't fall because of gravity anywhere. We don't have to take gravity, we don't have to take gravity into account because of this ball being kept on a horizontal surface, and we are seeing this entire system from the top, let us say. So this is in fact the top view. The surface on which this ball is kept is below this ball, and there is another particle that comes in, and this particle hits this ball somewhere. So first, if I draw a line that goes through the center of this ball and is going to be parallel to the horizontal surface, that's this line, and there is a particle that is traveling from here in the plus x-axis direction with a velocity v, and this particle has a mass m, small m, let us say. And just for this particular problem, let us also say that this ball has got a mass of small m also. So this is also small m. The only thing is it's spherical, it has got a radius r. The line along which the particle is traveling, this line is at a distance of rho from this particular central line that I have drawn here. So this distance here, in fact let me show you that distance in a different way. So this particular distance, this much, is equal to rho here, and this small object will come and it will go and hit this ball somewhere here. So when it hits the ball here, there will be a normal force acting between the particle and the ball that will be acting along this particular line. So I can say that the line of impact is then this particular line. Yeah, so this is how we usually define the line of impact, right? At the point of contact, if you draw a common normal, that will be the line of impact. Okay, so this is the line of impact. The center of mass of the particle is on the line of impact. The center of mass of the ball is also on the line of impact. So it is a central impact, cool. But then the velocity of this particle just before the impact is not along the line of impact. So it is not a head-on collision, it's an oblique collision. So this is an oblique central impact, and we want to figure out what will happen after the collision. So the question is, in fact it doesn't make sense to say that there is a frictionless surface of particle, but then we are just trying to say that there is no frictional force acting between the ball and the particle. And second, assume it to be a perfectly elastic collision, E is equal to 1. So these are the two assumptions that we have been given, and they are asking us to find out the velocities of the ball and the particle immediately after the collision. So what do we do? Any force that is acting on the ball, let's say, will be acting along this black line. So if you were to just draw the ball here, yeah, like this, and if you were to draw the line of impact again, then any force on this ball will be acting along that particular direction like this. This is how a force will act. And if there is a force acting on the ball along this particular axis, then the ball will suffer a change in momentum along that particular axis. So if it suffers a change in the momentum along that axis, it will start moving along that axis as a result of that impact. So figuring out the motion of this ball is actually pretty simple. It will move along this axis. I can also speak about some angles here. I can probably think about this angle as being theta, and I can find out the value of theta from the information that I have. I have the information that this distance is rho and the radius is r. So I know that in a triangle which I can draw here, I have got a distance r, I have got a distance rho. So therefore sine theta is rho by r. And so cos theta will become automatically root of r square minus rho square divided by r. So these are the two bits of information that I can have from this particular diagram. And in all such cases, what we have to do is we have to conserve the momentum along two particular axes, let's say. So let's take one axis as the line of impact and another axis as a perpendicular line. So I can call this probably the normal axis, and I can call the other one as the tangential axis. So I've got n axis like this, and then I am also going to take a t axis, that is probably this one. So this is the t axis, and along the t axis the momentum should be conserved, along the n axis the momentum should be conserved, fine, but that's for the system of the ball and the particle. What if you look at one of these objects individually? Let's just have a look at the particle individually. What happens to the particle? So if I were to draw the particle here, then you will see that any forces that the particle experiences are going to be along the n axis. There is no friction, so it's not going to experience any force along the t axis. If it does not experience any force along the t axis, then the particle's momentum along the t axis should be conserved. So that will help us to do something for the particle at least. For the particle, if I draw the velocities, just before the collision it had a velocity like this, and its value was v, and there was a component along the normal axis. In fact, I have drawn it too inclined, maybe this way, yeah, and that was v cos theta, because the angle here was theta, and the other component was v sin theta. So I know that v sin theta should be unchanged. This entire thing is the situation before the collision, and after the collision v sin theta is unchanged. So this particle should keep on moving along the tangential axis with v sin theta, and for all practical purposes along the normal axis I can treat it as a one-dimensional collision. So one-dimensional collision, two bodies of equal masses, we know that they will exchange their velocities after the collision. We know that. So because the masses here were equal, we can straight away say that. If the masses were unequal, then we will have to use the equations for the velocities finally after the collision in terms of the mass of this particle and the mass of this spherical ball. That has to be done, but this is an easier case. So since along the n-axis velocities are exchanged after the collision, therefore I can say that the ball, in fact first the particle, has got zero velocity along the normal axis after the collision, and the ball has got a certain velocity which will be equal to v cos theta after the collision. So this ball here has got a velocity v cos theta along the normal axis after the collision. So you see that again in this entire process the momentum has been conserved. Before the collision there was mv cos theta momentum along the normal axis. After the collision also there is mv cos theta momentum along the normal axis, just that the body that was moving along that axis has changed. and along the tangential axis it was mv sine theta before the collision, and it's mv sine theta after the collision also. So this is how you can probably solve. But then if you have to find out the speeds of these objects, so the speed of the particle after the collision is going to be v sine theta, which is going to be equal to v times rho by capital R, and the speed of this ball after the collision is going to be v cos theta, and I know the value of cos theta from there. So this is going to be v times root of r square minus rho square divided by r. So this is the final answer to this problem.